Okay, it's the second video out of the three-part series about the calculus review um, for semester one. And in the previous video, we did chapters 1 to 3, which included an introduction to calculus, limits, and a solid probably half of what derivatives actually entails. Now we're going to be talking about chapter 4 and 5. Chapter 4 is about mainly integrals. Chapter 5 goes more in depth into derivatives with some more tools and applications. So let's get started. First of all, what is an integral? Integral is basically a way to find the area under the curve. And the definite integral specifically is going to be expression that gives you the area under the curve, like an actual value, a numerical value that gives you the exact area under the curve of a function. And a definite integral has this symbol. This is the integral symbol, and the definite integral has bounds a to b, where a is the initial and b is the final position, of f of x dx. Now, what is this exactly? You can rewrite as the limit, and here's where limits come back, as n approaches infinity of the summation from k equals 0 to infinity of delta x times f of delta of a plus delta xk. This looks a bit familiar, doesn't it? This is the exact formula we use for the area under a curve using left endpoint, right endpoint, and midpoint rectangles. This, in fact, isn't exact same except for this infinity over here, which actually should be an n now that I think about it, because the limit as n approaches infinity. If we did not have that statement, you would put an infinity up here, which is mathematically incorrect since you're not supposed to put an infinity there, which is the entire reason we're putting limit as n approaches infinity in front of it. So it's not infinity up there, it's n. So this entire thing is just the using rectangles to find area, and then you just put limit as n approaches infinity. And what that does is, if you have big rectangles, it's going to be less accurate. So what it's saying is, why not have infinite rectangles? Just each rectangle is the height of the function at that point. That's going to give you a perfect estimate of the area. So a is called the lower bound, b is called the upper bound, and this is called the integrand of the integral. Some basic terminology. Why is this important? It gives us the area under the curve. Before we were just estimating it. Same with derivatives. Before we were just estimating using an average rate of change. But then we were able to use limits and find the instantaneous rate of change formula, which gave us derivatives. Same thing here. We're using Riemann sums, which is what they're called, the summation notation. The Riemann sums to estimate the area under the curve. Then we used limits, put that together, and got an actual area under the curve, the exact value using integrals. So again, I'm rushing through all the material since it's an entire 4 months worth of material in just 3 videos, and 2 even for AP Calc AB, which is why I didn't cover some of the other stuff. I mentioned in the previous video that I was going to cover horizontal asymptotes and how limits have to do with that. I wasn't able to because we were short on time in the end, and it wasn't that important to the curriculum. It was important, obviously, but some of it was in pre-calculus. So if you learn in pre-calc, you're good. But I digress. Back to this. I won't be able to cover absolutely everything that we learned in class. Instead, I'll be able to highlight the key concept, especially what we learned in math notes, because that is basically the most important things we learned. So what's next? Well, definite integrals. There's some properties of definite integrals that we can do to simplify some expressions and so on. First of all, the integral from a to b of f of x dx. And look at this notation right here. The dx is important because it's always in an integral. It's basically representing a small amount. I should probably talk about this. So this is representing the start to the end of the function. This is the height of the function at a certain point, and this is the width of the rectangle, basically. And that is basically approaching 0 because n approaches infinity. So this is still the area formula of a rectangle. height times width. Width approaches 0, height approaches basically like the value of the function at that point, which is why it is a limit. But back to the properties of definite integrals. So this is equal to the negative integral of b to a of f of x dx. So basically you can just switch the bounds and you just have to take the negative of the integral. Second one, integral from a to b of k times f of x dx. You can move the k outside and you're going to get k times integral from a to b of f of x dx. Third one, integral from a to a of f of x dx is equal to 0. Basically saying if you're just talking about one point from a point to itself, it's going to be 0 since there's really no area. It's just itself. And then we have integral from a to b of f of x dx plus integral from a to b of g of x dx. So you have two different functions, but on the same interval. You just add them in the same integral. You can combine it into one integral, f of x plus g of x dx. So that's the first 4 properties. There are 2 more that are a bit more interesting. The first 3 are like basic properties. Number 4 and 5 are simplification properties. So what I mean by that is number 5 is integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. So basically saying, basically saying if you have the same function over 2 different integrals that are adjacent to each other, you can add the intervals together. And last but not least, the probably most confusing one, if you have a plus c, a plus c and b plus c as the bounds, and you have f of x minus c dx, this is basically equal to integral of a to b of f of x dx. Another way to think about it is, if you translate the actual function horizontally to the right by c, that's what this is doing. You also increase the bounds by that same c. If you translate it horizontally to the left by c, you decrease the bounds by the same c. So 6 properties of integrals, definitely worth memorizing, or at least understanding how they work so you can apply them to problems, because there is probably going to be a problem on the final about combining definite integrals. Moving on, still talking about definite integrals, actually. Definite integrals with variable bounds. So basically, we've been talking about like from 2 to 3 of x dx, right? We still don't know how to evaluate that, though. And that's what we'll be talking about in the next section. But we need to first talk about variable bounds, because that'll help us later. If this is the case, it's not that hard to evaluate because these are numbers. We can plug them into whatever formula we'll learn later. But what if it's something like from 2 to t, and the integrand is x dx? What would we do then? What it's basically saying is you're going to treat that as a number and just end up with an expression with t in it in the end. Now, what expression would that be? Finally, we answer the question of how to calculate this. Hint, it has to do with derivatives, but the opposite of derivatives. we're going to use antiderivatives, which we talked about in the end of the previous video. It's undoes a derivative. So what's the antiderivative of x? It's going to be, since it's x to the power of 1, it's going to be x to the power of 2 in the antiderivative. Then you divide by this new power we have, 2, and we're going to get 1/2 x squared as our antiderivative, plus c. Never forget the plus c. Just like you never forget the dx here, never forget the plus c here. Now, what does that have to do with definite integrals? Well, what we do is we basically take this expression, that's our antiderivative or our general antiderivative, and we can ignore the plus c in this case since it's a definite integral. Then we draw a bar and write our same values, and we just plug in the upper bound into this, get some value, plug in the lower bound, get another value, and subtract them. So let's do an example. You plug in 3, you get 3 squared is 9, and 9 over 2 is just 9 over 2, or 4.5. Now you plug in 2. 2 squared is 4, and 1/2 of 4 is 2. So you get 9 over 2 minus 2. You simplify that, and you get 5 over 2, or 2.5, as your answer for the integral. Now, variable bounds. Let's try that same thing. It's going to be 1/2 x squared from t to 2, or from 2 to t, since 2 is the lower bound. And that's going to be equal to, you plug in t and you get t squared and divide by 2. So t squared over 2 minus, and when you plug in 2, you're going to get the same answer, 2. And we can't really simplify much further. So this is going to be your answer. Note that there's no plus c since it was a definite integral and we technically did evaluate it. Even though there's a variable expression at the end, it's not the variable that was in the integrand. It's a variable that was in the bounds. So this would be the expression we get from this. This leads us into indefinite integrals. We talked about definite integrals. Let's talk about indefinite integrals. Basically, no bounds. We just have integral of x dx. This is the actual part where the antiderivative comes in because it represents all the antiderivatives. And this is just going to be the general antiderivative. And then don't forget the plus c since it's an indefinite integral. Now, the general antiderivative of f of x dx, like we said in our last video, is going to be capital F of x plus c. So that's indefinite integrals. We gave one example of that. The way indefinite integrals relate to definite integrals is that you use the indefinite integral to get the antiderivative, and then once you get the antiderivative, you plug in the values from the definite integral to get your total area under the curve. That was all a bunch of definitions and properties and things about definite and indefinite integrals. Let's talk about a few theorems. Like I said, the intermediate value theorem was not one of the most interesting theorems. The fundamental theorem of calculus is pretty interesting, though. There are two parts. The FTC, it's abbreviated using the FTC, fundamental theorem of calculus. The first part of it says, when you take the derivative of the integral from any lower bound, a number a, to x is a variable in the bound, which is why we learned about that, of f of t dt. So before t was in the bounds and x was in the integrand, but now t is in the integrand and x is in the bound. The reason why is because we want an expression that ends with x because x is the one we're more familiar with. Not really that big of a deal. This is going to be equal to f of x. What it's basically saying is the derivative undoes the integral. And note that it's f of x and not f of t because x is in the bounds. T is just a dummy variable in this case. That's why we wanted x in the bounds rather than in the integrand, because the ending expression would be based on the variable in the bounds. Now, the FTC doesn't say this, but I do want to make this clarification. This is not the same thing as integral from a to x of d dt. Remember ddt, because this function in here is based on t, not x. So it's d dt of f of t and then dt. This is not the same. when we talked about functions and inverse functions, we could switch the order because it didn't matter, but here order matters because our answer is going to be f of x plus c. The reason why is because we're ending with an integral. We're first taking the derivative and then ending with an integral, meaning no matter what, we need a plus c. And actually, technically speaking, this answer is going to be constant. I meant if there were no bounds, it would be f of x plus c. Because, and this is usually the more common one, because if you had bounds, then it would just be either a variable expression or it would be a constant. Now, why are they different? Why does this not have a plus c? Because it does the integral first, and you get f of t plus c. And then you take the derivative of that, which gives us this. And the constant goes away because when you take the derivative, a constant becomes 0. That's why in this one, there's no plus c. The second part of the fundamental theorem of calculus basically is something we kind of talked about before. When you take the definite integral from a to b of f of x dx, you take the antiderivative, and it's going to be the capital F of b minus the capital F of a. We just talked about this here. That's how we found our answer is 5/2, because we took the antiderivative, which is f of x, then plugged in b and a and subtracted them. So that's just a formal way of what we said. That was the fundamental theorem of calculus, probably the biggest thing to know in chapter 4. And we only have one more section left in chapter 4, but this is a relatively harder section, I would say. So we're actually flying by through this. I'm not going to even start chapter 6 though in this video, even if we have time, because chapter 6 is strictly BC topic, and I don't want AB students to be confused if there's some BC topics in an AB video. And obviously BC would also watch this video, but they would also watch the next video. But I digress. Next section is area between curves versus area under a curve. Area under the curve is an accumulated value. Like that. It's accumulated over time, and I'll explain what I mean by accumulated value later when we're talking about word problems related to integrals. However, area between curves is more of a geometric area. If you have x squared and just x, and you're trying to find this area between the curves, you would use a geometric area rather than, there's barely any word problems with area between curves. Now, the formula for this is integral from a to b of absolute value of f of x minus g of x. Why absolute value? Because without seeing a graph or like solving for stuff, we don't know if f of x is on top or if g of x is on top. If we do, then yes, we can remove the absolute value and just put whichever's on top first, whichever's on bottom second. Like, let's say the line was g of x and the quadratic equation was f of x, then we would replace this with g of x minus f of x because g of x is on top in this case. You cannot really establish an antiderivative for an absolute value by hand. You could use a calculator, of course, with this, which is why if you're doing it in a non-calc section, you're going to need to find out which one's on top. You need to find out what the bounds are, and then you put the integral in that form. There's one difficult topic in area under the curve, that area between curves, that I'm not going to cover, because even if it does appear on the test, it's going to be in a limited fashion, and I don't think it's that important. It is harder than this because it's area under the curve using horizontal rectangles, and it is important for second semester when we're talking about volume based on curves, like volumes of rotation. But I will get to that when we get to semester 2. For now, I'm going to be talking about word problems with area. Area under the curve is also an accumulated value, and the reason why is because let's say you have a function that says that the rate at which a barrel of water is leaking is r of t is equal to t squared plus 4. Find how much gallons of water leaked out in the first 5 minutes. How are we going to do that? Well, if this is the rate function, the integral of r of t is going to give us the amount function. And that's what I mean by accumulated value. The integral, or area under the curve, of a rate function gives us the accumulated value. So integral from 0 to 5, because we want in the first 5 minutes, of r of t dt is actually going to give us our answer. What is it, though? First of all, let's take the antiderivative of r of t. Since r itself is a capital letter in this case, we can't really denote it with a capital R. But I'm just going to call it a of t for amount. This is going to be, let's take the antiderivative of t squared. T squared, you add 1 to the exponent and make it t cubed. And then what you do, you divide by this new power. Since the coefficient was originally 1, it'll be 1/3. So 1/3 t cubed plus 4 antiderivative of constant, which is that constant times t, or x, whichever variable you're using, so 4t, and then plus c, but since it's definite, we can technically ignore that plus c, and all we want is, well, this is the function, so I still have to put plus c, but all we want is this. We want 1/3 t cubed plus 4t, and then a bar, and then 5, 0. And then we want to calculate that. So we plug in 5, we get 1/3 times, well, 5 cubed is 125. So 125 over 3 plus 4 times 5 is 20. And you can combine this into one fraction, which I would definitely do. Over 3, you're going to get 185 over 3. So that's the first part. And then you have to subtract when you plug in 0. You plug in 0, you get 0 plus 0. Pretty easy. You minus 0, and you're just going to get your answer as 185 over 3. Sorry, not 185 over 0. And what's the units for this? Well, this was in gallons per minute because we said it leaked out. We want to find the amount of gallons in 5 minutes, meaning it was in gallons per minute. So this would actually be in gallons because it's an amount function. We want to find the amount, so that's in gallons, not gallons per minute. So that's a pretty simple integral word problem having to do with accumulated value. And that's basically all the important topics that were covered in chapter 4. That basically talked about definite, indefinite, and other types of integrals, including word problems, fundamental theorem of calculus, and area between curves. And now we're on to chapter 5, which is a lot of in-depth applications and tools of derivatives that we didn't learn before. All we learned about was the power rule, and then some applications in chapter 3, and now we're talking about a few more rules as well as more applications. Now, the textbook starts off with a few more applications relating to curve analysis, and then moves on to some of the rules we need to use, and then back to applications with optimization. However, I'm going to start off with the rules because I personally find it easier to learn tools before applications because you use the tools in application. I'm just going to run through the 3 main rules that you need to know for chapter 5, the product rule, the quotient rule, and the chain rule. Product rule, if you have the derivative of a product of 2 functions, f of x times g of x, your answer is going to be f prime of x times g of x plus f of x times g prime of x. Similarly, if you have the derivative of a quotient of 2 functions, it's going to be actually a bit more complicated than with a product. It's going to be f prime of x times g of x, similar starting, minus f of x times g prime of x over g of x squared. So a bit more complex. Order actually matters in this because there's a minus. Here, order did not matter. But yeah. And then chain rule, if you have a composition of functions, f of g of x probably the most simplest rule here, although it might not be the easiest to understand. It's going to be equal to f prime of g of x times g prime of x. And I am going to go through an example with the chain rule since it's probably the most important one. But let's try the derivative of square root of x cubed plus 1. So let's look into the square root of x. What's the derivative of square root of x? Well, that's just x to the power of 1/2. So you bring down the 1/2 and subtract 1, and you're going to get 1/2 times x to the power of negative 1/2. And if you were to write that without like fractional or negative exponents, it would be 1/2 root x. So that's the derivative of the outer function. So we know it's going to be 1/2 root, and then you plug in the inner function here. That's what it means when it says f prime of g of x. You take the derivative of the outer function if there was just x in there, and then you plug back in the inner function. So it's going to be 1/2 times the square root of x cubed plus 1. And you multiply this all by the derivative of the inner function, which is x cubed plus 1. Derivative of x cubed is going to be 3x squared. Derivative of 1 is going to be 0. So this is just going to be 3x squared over 2 root x cubed plus 1. And that would be your answer. I'm also going to talk about the derivatives of the 6 trigonometric functions. And I think a table probably explains it best. You have sine, cosine, tangent, and then you have cosecant, secant, and cotangent. There are other ways you can organize the table as well. You can do sine, cosine, tangent, cotangent, cosecant, secant, cosecant. You can honestly do it either way, and that probably shows you a pattern better, but this is in order in most cases. Like you usually go sine, cosine, tan, cosecant, secant, cotangent. Derivative of sine is cosine. Derivative of cosine is negative sine. That's kind of simpler. But then derivative of tangent is going to be secant squared of x. And derivative of cosecant, cotangent is going to be negative cotangent squared. So I'm going out of order a bit. But cosecant and secant are some of the more complicated ones. So I'm actually going to go this way. And sorry, not negative cotangent squared, negative cosecant squared. So that's going to be the derivative of cotangent. And you can probably see a pattern building up here. You basically take the co-function for the other derivative. So if you have sine to cosine, the co-function of sine is cosine. So you take the co-function of the derivative. So sine to cosine, it's going to become cosine to negative sine. So there's also that negative involved. So tan to cotangent, that's the co-functions. So you have secant, and you take its co-function, which is cosecant, and then add the negative in front. Finally, for secant is going to be secant times tan. And as you might expect for cosecant, it's going to be negative cosecant times cotangent. That would be your answer. For all 6 trigonometric functions, those are the corresponding derivatives. Take a moment to probably memorize this or understand how to derive it. Now, all we have left in chapter 5 are applications. I won't go too in detail into the first application, which is curve analysis. We already went over that in chapter 3 or in the previous video. But one thing I did want to note are extreme values and critical points. So extreme values are basically like maximums and minimums. And there are 2 types, global and local. Global, also known as absolute, versus local, also known as relative. So if you have a function like this, this is a global maximum, this is a local maximum. So imagine this is actually lower than this, which it should be. It doesn't really look like that. This is a global minimum, this is a local minimum. Global minimum is the absolute minimum value. And if it goes to negative infinity, you can ignore that. So it's basically going to be like the lowest extreme point, or extreme value. And this is going to be the highest extreme value. And then locals are little bumps, basically every single other extreme value. Critical points, on the other hand, are also extreme values. So they're very similar. It includes both global and local extreme values. So the reason why they're useful is because it helps you understand the behavior of function. Like we said, when the derivative is 0, that means there's a critical point. So we didn't really use that language. We just said when it changes from positive to negative, it's going to be a maximum in the original function. And when it changes from negative to positive, it's going to be a minimum in the original function. Now we're saying if it's just 0 in general, it's going to be a critical point for the original function. Let's talk about the different derivative tests. There are 2 of them. The first one is the first derivative test. And it basically says, let's say you know that f prime of x is equal to 0. How do you know if it's a maximum or minimum? You might say, oh, if it changes from positive to negative. Yeah. But what if you don't want to do that? Well, the first derivative test is actually very similar to that. What it basically says is you want to take something a little less than x, and you want to take a little something more than x. So f prime of x minus a, you take the sign of that, and you take f prime of x plus a, where a is a very small amount, like 0.5 or 1 or something like that. And if it's greater than 0 and then less than 0, it's going to be changing from positive to negative, which we already know means it's a maximum. If it's less than 0 and then greater than 0, it's going to change from negative to positive, which we know is a minimum. So that basically is what the first derivative test says. Second derivative test is my personal favorite. If there's a choice, I would use the second derivative test. And the reason why is because instead of finding 2 different values, you only need to find 1. Let's say you know that f prime of x equals 0. You use the second derivative, which we know tests concavity. From chapter 3, we learned that f prime of x. So you don't even need another variable a that is a small amount. You just use the same value itself. If f prime of x is greater than 0, that means it's concave up, which means it's a minimum. Versus if f double prime of x is less than 0, that means it's concave down, so it's a maximum. I would definitely use this if possible because it simplifies it a bit. And although you do have to find the second derivative, which is a little bit more work, I don't think it's as much work as the first derivative test. The final big thing we have to learn is optimization. And then after that is L'Hopital's rule, which is not that bad. Optimization is probably going to take a while, though. I'm going to start off with an example problem instead of the actual process itself, because like I said in a previous video, I think learning by example is probably one of the better ways to do it, if possible. So let's do an example. Let's say you have 300 feet of fencing. And you want to create a rectangular enclosure. And you have the barn, which provides one wall of the rectangular enclosure. Meaning you only need fencing for 3 sides of the rectangle, and the 4th side is already by the barn, so you don't need that. If you want to find the maximum area possible in the rectangle, what dimensions should you use for each side? So how do we do this? Let's set x to be these 2 sides, since they're equal, since it's a rectangle, and this is y. What we can do is we know the sum of these has to be 300, since that's the maximum amount of fencing you're given. So 2x plus y equals 300. Note that it's not 2x plus 2y, which is the general formula for a perimeter. Since we're ignoring this fourth wall, it's already, it's not part of the fencing. It's part of the barn. Now, what you can do is you can solve for y in terms of x, kind of like a system of equations. You just subtract 2x from both sides and you get 300 minus 2x. So that's what y is equal to. Now, how do we use this? Well, we know the area of a rectangle is given by xy. So if you were to write this as a function in terms of x, what you would do is x times y, but since y is not in terms of x, you replace it with an expression in terms of x. So x times 300 minus 2x. And therefore, f of x is equal to 300 x minus 2x squared if you distribute. Now what? Well, we want to maximize it. What do you think of when we hear the word maximum? Well, derivatives. When the derivative is equal to 0, and we can use the second derivative test to make sure it's a maximum, then we know that this has a maximum, and we can find out the maximum area possible and the dimensions required for that. So what's the derivative of this? F prime of x. So 300x is just going to be 300. And negative 2x squared, you bring down the 2 and you're going to get negative 4x. Let's set this equal to 0 because that's when we have a critical point in the actual function itself. You have 300 minus 4x equals 0, and therefore 300 is equal to 4x. You divide both sides by 4 and you get x is equal to 75. Now, is that a maximum or a minimum? You could guess, but it's always better to double check. I always suggest double checking because it could be a minimum, meaning there's something else you have to do. So you take the second derivative, 300 becomes 0, negative 4x becomes negative 4, and it's always going to be negative. And we said that if it's less than 0, it's a maximum, meaning it indeed is a maximum. No matter where on this curve, it's always going to be concave down, meaning it will be a maximum. Therefore, this gives us the maximum x value. Now, what about the y value? Well, you plug it back into this expression to find y. 2 times 75 gives you 150. So 300 minus 150 gives you y, which is 150. So your answer is going to be x equals 75, y equals 150. That was a relatively simple problem of optimization. There are some harder problems involving volume and surface area. This one does involve two variables, x and y. There's some that only involve one variable, but the basic process is I like to draw a picture to make sure you define the variables correctly. You write the equation that you need to optimize, so that's going to be xy, the area equation. Then you write other equations that you need, the perimeter equation in this case. Then you write a function given the equation that you need to optimize. So basically you write xy, you use this other equation, and then you create this function f of x just in terms of x. Finally, you optimize using calculus, get your answer and make sure it's actually what you're looking for, and then you just answer the original question. Because we got x equals 75, that's not the final answer. It asks for the dimensions, meaning x and y. So that's going to be our final answer. We have to answer the original question. Final thing for this entire video, L'Hopital's rule basically says, let's say you have a limit as, let's say x approaches 0 and sine x over x. You might get deja vu over here. We talked about this in our first video when we were talking about limits. We said limits of some trig functions you should probably memorize. This we said was equal to 1. Why though? So L'Hopital's basically says if you have 0 over 0, you can take the derivative of the numerator and the derivative of the denominator and then rewrite it as a new limit problem. So you write limit as x approaches 0. What's the derivative of sine? We said that was cosine. And derivative of x, we said that's 1 because power rule. So it's just a limit as x approaches 0 of cosine x. And now you can just plug it in and you get cosine of 0, which is equal to 1. And that proves us that this limit is equal to 1. So that's basically what L'Hopital's rule says. It says if you have an indeterminate form, or 0/0, you can take the derivative of numerator and the denominator and then simplify it and rewrite the limit and then evaluate. Sometimes you have to do it multiple times, which is a bit tricky, but not that bad. Final thing I do want to mention, what if it's infinity over infinity? Then there's something called the dominant terms method, which we talked about a bit in pre-calculus, the raised to infinity, for example. Let's say its limit as x approaches infinity of x squared over 2 to the power of x. Exponentials will always beat polynomials. Polynomials will always beat logarithms and so on. So since exponentials beat polynomials, the denominator is going to be faster, and therefore it's going to be going to infinity faster, and therefore this limit would be 0 because it's going to be something over infinity, which is said to be 0 since it's a limit. So that works for infinity over infinity. This is for 0/0. And yeah, that's basically it for chapter 5. We went over some derivative tools and applications, and then we went over chapter 4 earlier in this video and talked about integrals. So that's it for Calc AB, actually. If you watch these 2 videos, you're done. But Calc BC, there's 2 more chapters, chapter 6 and chapter 7. And the third part of this series will be released soon with the BC stuff that you need to know. So that's it for this video. And for the BC students, I'll see you in the next video talking about some more derivative and integral applications and tools. And then chapter 7 is even more things to do with them. So, just going in depth on stuff. So I'll see you then.